and they have no gliding parts, or nearly no gliding parts. Another aspect is why we think the plants are immobile. And should I stop, perhaps?
We just had a problem with the microphone.
Okay.
We weren't hearing you very well on the video conference. So Anthony's changed something and we're just finding out whether that's better. Sorry, Tom.
No problem at all.
Okay, great.
Is it better now?
Yes. Yeah.
Okay, I hope you have at least heard part of what I have told. And the big difference to plants is, as I said, they have no localized hinges, no gliding paths, no wear. Most movements in plants are caused by elastic deformation of delocalized structures. But why don't we realize plants as moving organisms? And the reason is, here you see a photo of tropical rainforest in French Guiana, where I work a lot, and it looks already relatively dynamic. But the reason is that the visible changes in positional stature during plant motion typically are either very slow, like growth processes, they take place in the time scale of hours, days, weeks, or even months, or they are very fast, like in carnivorous plants, where we worked a lot of it, in milliseconds, and both makes it hard, if not impossible, to recognize by our optical system. I will show you quite a few examples. These are slow motions. Here you see growing plants in tropical rainforests, stolen from a movie of David Attenborough's Secret Life of Plants, and recommended. Have a look on it. This is from our own work in the middle. These are autonomous movements of lianas, liana tendrils looking for support, and the other one also comes from our place. This is an opening pine cone where we did a detailed study on. Very slow. We don't see them as motions because they are too slow. On the other end of the list, we have carnivorous plants. Here you have the infamous Venus flytrap. Here you have a special species of sundew, Drosera glandulifera. Here you have the water trap, and they all take place in these three species around 100 milliseconds for snapping. Much faster is the bladderverse urticularia, which sucks in its prey in less than half a millisecond, and the acceleration of the prey is 3,000 g. So 3,000 times the Earth's acceleration, the gravity acceleration. And this is a fast movement we have in plants. This is a spore propulsion, spore discharge, which takes place in about 20 microseconds. So plants are very active, very dynamic, but we just don't see it. But it's worth to have a closer look. And time lapse, as you see in the upper part, or high speed camera makes it visible for us. First, I want to show you what we did in bioinspired architecture for phase changing systems, and we got inspirations. These are all the plants we looked at over the last 10-15 years on the motions, and I will concentrate now on my first example on a flower. This is a bird of paradise flower. This was inspiration for a phase changing system, and the Alprovandus. This is the water wheel plant or the water trap. Let's have first a look at the bird of paradise flower. This is a bird of paradise flower. It's pollinated by birds, it's by sunbirds or weaver birds, and they land on a perch. And I hope you can see my hands. The perch is a cylinder which is open on top. It's formed by two petals, and as soon as the bird lands on it, by the weight of the bird, bends down and opens. And it's an elastic motion. It's interesting. It's a so-called torsional buckling. And torsional buckling is a type of failure, which you learn in the first term lectures of building construction to avoid it, because this is why thin shells fail, but nature has functionalized it, and this is really great, and I will show you exactly what's behind it. Here you see a nice video, and you see the opening of the perch, and the yellow stuff is the pollen, and by opening the perch, the pollen can be placed on the feet of the bird flies to the next flower and makes the pollination, because the bird wants to feed on nectar, which is at the base of the flower. Okay. What's interesting, we did tests how often can we open this perch, and we can open it with nearly exactly the same force displacement curves you see here, 3,000 times. We just stopped it, and it was after 14 hours, and my postdoc said you can do what you want, but I go home. You probably go for 5,000 watts. Interesting, only the first 5 are need a slightly bit higher force, about 0.1, 2, and the rest is always around 0.07, 0.08. And interestingly, if you calculate the weight force of a typical pollinator, a cane weaver, then it's about 5 times higher than the force needed to open. So each time cape or sunbird, which is even slightly heavier, lands on the flower, it will open. Don't ask me why it can be opened 3,000 times. We don't know the biological meaning because from field observations we know that maximum, I would say, 50 to 70 times a flower is visited by a bird, typically below 30 times. And I think it's a wonderful example for us that the structures are so clever, so good designed by evolution, that you can do much more than it's really necessary. And perhaps it's a kind of level of pre-adaptation where something can evolve out of it, which you just don't know yet. Anyways, what did we do? We looked in detail on this perch. We made a cross-section, and you see here it looks very complicated. I just want to show you, biomimetics has a lot to do with abstraction. We removed the style, but what you see here on one side, you have a pedal wing, which is more or less a stick-like structure. It's very stiff, and you have a membranous structure. Then you have again a membranous structure, stick-like structure, another small membranous structure, and a stick-like structure, and the same more or less mirrored on this side. So you have 6 subsystems, which all consist of a rib-like structure, which is rather stiff, and a membrane. And if you look, it's really fascinating. The membranes are less than 100 microns thick. And they survive without any fatigue, without any failure, 3,000 opening and closing cycles. I think this is really nice. What we did then, we abstracted and we said, okay, what do we need? We need just one of these subsystems, a stick and a membrane. And this is what we did then. We did FAM simulations with our colleagues in Stuttgart. We made the first functional model. And what you see down here is the first functional model which really works together with the company. And what looks like we would turn it with a gliding part. This is not the case. The only thing we do, we bend the backbone, and by bending the backbone in this thing, which is about 2.5 meters high, by bending the backbone about 2 centimeters in the center, it opens and closes by this torsional buckling. So you have no gliding parts. You have nothing which you have to look at, or nothing where you have to put oil in or so on. Next thing is, we went on and made a double flective fin, where we have 1 backbone and 2 membranes, so we have only 1 actuating time thing. And then we made a patent in 2012, and in the same year, slightly different, but it's the same principle. It was built in South Korea, in Yeosu, at the World Exhibit, and these are this kind of flectifold membranes up to 14 meters high. And they are beautiful, and the architects like it because they say this building breathes air. Because it's really, and here you really manage not only to really transport the function, but also to transport the aesthetics of the biological role model. But I have to pour a bit water in the wine. I'm happy with it, but I could be more happy. What I doesn't like is you need relatively high hydraulic pressures to bend them, especially the large ones. That's not as good as in the biology, and the other thing is you have a geometric restriction. They have to be 7 times longer than wide. And therefore, we said, okay, let's have a look. Perhaps there's another example, and this is a water trap. A water trap is a sister to the Venus flytrap, but as you see here, the Venus flytrap makes a curvature inversion. If you look from the outside, if it's open, then it's concave, and then it snaps in. And it is only 2 states, 2 stable states, open or closed. And this is not good for a sun-shading system because we won't have all the states in between. And therefore we looked at the water trap. It's a sister of the Venus flight, but has a totally different kind of actuation mode. What does the water trap do? The 2 halves remain undeformed, but the closure is driven by hydraulic deformation of this part here. This is a midrib, it's a leaf, and this is the 2 leaf halves. And it's a hydraulic deformation of the midrib. And this hydraulic deformation of the midrib via motion amplification causes the closure of the trap. And it's interesting, it's even faster than the flytrap, Venus flytrap. Again, just to show you, if you look at the biological examples, they look tremendously complicated. And the reason is they do not only open and close, they have to digest, they have to sense, they have to do a lot of things, decision making, but you have to really filter out the secret behind it. And the secret here is you have the backbone, this is midrib. What you have on the midrib are the glands of no interest for the satiating systems, and you have 2 motor zones here. These are cells which change their turgor pressure if there is a sensor, and then they bend the backbone. Having this in mind, we said, okay, we have to transfer it. And what did we do? We found out that it's much easier to transfer it with a lens-shaped actuating system where we have two curved folds, and then we have to bend the lens-shaped situation, and then it's opening and closing very quickly, and we can observe, we can put surface, climber and decliner. Then we played around, we did a lot with our colleagues in Stuttgart, a lot of FEM simulations. You see, it's much simpler and cheaper to make simulations than to build everything, even with 3D printing. And what we did here, we tested how the different curvature influences the hinge stress and the pressure you need. This is a high curvature, and this is a sequentially smaller curvature. And you see, if the curvature is small, you need less pressure, but you have higher hinge stresses. So you can play around and do it. The next things we did, used it together with the ETV Denford, one of the world's greatest textile technical institutes. And it's very simple. It's a ragged structured laminate system with stiff and flexible segments, and it can be produced in one production process. What do we have? The PVC is just for filtering the UV out if it's outside at a building. Then you have glass fiber reinforced polymers, and you have elastomers in. In the stiff parts, these are the wings and the central lens-shaped structures. You have a lot of glass fiber reinforced polymers in. In the flexible parts, these are the curved folds. You have nearly only elastomers in. And we are pretty happy, it worked, wow, wow, wow. And then we found out it only works about 100, 150 times. Then we have problems with the hinges. The hinges start to break, which is no good because in architecture, it should run at least 20 years. You can calculate it's about 10,000 to 20,000 opening closing processes. What did we do then? We asked our colleagues from the animal departments in Tübingen, and the colleague worked on beetles. And he said, oh, have a look on the hind wings of beetles, or here on a bug. This is an Italian strip bug, Prophyssoma italicum. They fold and unfold their wings several hundred up to 1,000 times. Have a look how the folds are made here. And the folds are bulgy and slightly, let me say, they have a slight kind of structuring in the fold additionally. And with this in mind, we could change, remodel our folds, and now it can open 10,000, 50,000 times. And it's typical for biomimetics. We have not only one role model, we have often 2, 3, or 4, where you borrow all the ideas from different groups here, plants and bugs. What if you do then? You build the first demonstrator, it's 50 centimeters on each side, and it's actuated by a pneumatic cushion. Here it's Speck, the red one, with a very slight overpressure, only about 50 millibars. And it can cover each kind of glider and anti-glider surfaces in buildings without gaps in. This is perfect. What we did next, we made a demonstrator with about 24 elements. This was at an exhibit in Stuttgart, and it's really beautiful. A colleague of mine said it looks like pigeons which have landed and flaps their wings. It's a bit more too poetic for me, but it's really beautiful. And what we did then, we should have built last year one in the Arabic Peninsula, where they are very interested in these open tent-like structures, but Corona stopped it. So perhaps we can do it next year. But what we definitely will build next year is a demonstrator in our greenhouses. Here we have the flect fold. Here we have the flect fin on the other side, and here we have a conventional non-mobile one. And we have all test devices in to see how good or how much better, which we hope, our system is compared to a traditional one. These are the two facade shading systems which were relatively well known, inspired by plants. The next example, and for the next example, I have to give you a slight tour into growth processes in plants, motion processes. You have the so-called Hobistic plant movements, phototropism, geotropism, thigmomorphism, and they are typically mediated by growth processes. Then you have elastic plant movements, the same thigmonastism by touch, seismonastism by shaking, hydronastism, photonastism, and they are typically mediated either via turbo changes in the parenchyma cells or via draw or wetting processes microscopically. What is the difference between these two growth processes? The stimulus is always vectoral. The stimulus comes as a vector. It's light, gravity, you can physically it's a vector. And tropistic plant movements go in the direction of the vectorial stimulus or away from it. So they always have also vectorial reaction. So here in this nice orchid, the flower and the leaves go to the light, the roots go away from the light. This is different in plastic plant movements. Nasty plant movements always make the same movement independent from the direction of the stimulus. They are pre-programmed, predetermined by the structure and the form of the reacting organ. And this makes them very, very interesting for technical devices, because you want to have a technical device which just always is at on level first, level one. You want to have a technical device which always does the same if a stimulus comes. If you push the gas in your car, you want that the car accelerates. You don't want that the car turns around or whatever. And this is easy for us. Therefore, first we looked at nastic plant movements. I will give you an example where we also try to combine nastic and tropistic movements in our system. I will give you several examples which are based on 2 role model types. One is stem structure of attachment of climbing plants, which are a real treasure trove for inspiration. I work a lot of climbing plants since many, many years. They grow in Montpellier. Lianas are so to say our pets from the plants, and with microscopic plant movements which are still sparsely studied. Concept generators. Let's start with the lianas. And let's ask, why are lianas so successful? Lianas exist in more than 130 families of seed plants and are prime role models for adaptive pre-programmed interactive material systems and structures. Lianas have evolved probably more than 500 times independently. It seems to be a very clever growth setup, with little invest of material, using other structures for support, and covering. New result shows that the leaf mass of lianas may be equivalent to the leaf mass of trees in tropical rainforests. Really abstract, and all lianas start from self-supporting predecessors. That's why I like them. And there are 2 questions. One question is in the early phase of liana. My question always is, what has a plant to do to become a successful climber? And what can we learn from soft robots or other plant-inspired materials? The first thing is, in the searching phase, when they're young, they have to reach and find a suitable support. They have to bridge a distance to establish on a new distance support. And as soon as suitable support is reached, they have to attach safely. 1, 2, 3. And all lianas do that. As soon as they are attached, they change tremendous mechanical properties. Young lianas stems are extraordinarily stiff. They are much stiffer than twigs of trees of comparable diameter, because twigs of trees go with the wind. They make a kind of wind escape thing, a wind lining, streamlining, but lianas are very stiff. And as soon as they are attached, they tremendously change the structural and mechanical properties. They become totally flexible. And this causes internal strains, which cause internal fissures. And these internal fissures have to be repaired. I will come back in a minute to that. But let's start with the young phase. What do plants do to reach and to find a suitable support? They make these wonderful motions. They are a subgroup of nastic motions. They are so-called autonomous motions, because they not even need a stimulus. They always do exactly the same, but they do it even without stimulus. You can even keep them in a dark room and they start to do it. Therefore, it's a subgroup of nastic movements, autonomous movements, and they can really cover a huge space volume to find supports by doing these things. And sometimes it's like a ballet. It's fantastic. It's really great. I think for me, I have this last movie. I have about 5 minutes long, and I'm really a bit stressed. I'm watching it after 1 or 2 minutes. I said, "Oh, great! It's really nice. It's really relaxing." So I can send it to you as a medical prescription. Yeah. It's really helpful. The next thing is, how does it bridge a distance to establish a new distance support? And this is the actual work we are doing at the moment together in a European robot group with IIT Pisa, Barbara Matzma, and many other groups, and we try to find out how plants. They do, they form braids. So single searches intertwine in braid, you see here, different species which are not about close braid, they form braids out of 2, 3, 4 of these things, and by this braiding, they can extend the reach. Interestingly, they don't do the braiding mostly horizontally, they do it vertically. And at the base, here you see Dipladenia, 1, 2, 3, 4, 5, and it's a bit like the Eiffel Tower. They have a very stable basement. And by this, they can go very, very high, and then they topple over, and then they find a new support. It's a very interesting thing to do. And we analyzed. What did we do? Here's Dipladenia. 1 stem, 2 stems, 3 stems, 4 stem. Mechanical properties, you measure the bending stiffness with 3-point bending. On what did we find? It's increasing from 8 Newton per square millimeter for 1 stem to 75 for 2 stems, to 180 here for 3 stems, 530 here for 3 stems, and 1650 here for 4 stems. So it's a tremendous increase by a factor of 10 for 2 stems, a factor of 22 to 67 for 3 stems, and a factor of over 200 for 4 stems. And now we want to understand what's going on, and I'm by training a biophysicist, and biophysicists try to make their life easy. So we thought, okay, what can we assume to make it calculable, and what can we get rid of from this complicated biology? What we did, we say, okay, we make a couple of assumptions. First is, all the stems have the same diameter in the braid, which is true for this segment. For this segment, or true, good approximation for the segments. The next thing is, they all have, in these interbraided parts, the same distance from the center of gravity of the entire system. And the next thing is, they don't slide against each other because they're fixed at these points of close entanglement. This we have tested by just putting a drop of glue on these places, and they are really, it doesn't change anything. We did a very, very simplified mathematical model. We calculated the actual segment moment of area. I don't know how far you are knowing about mechanical properties and stuff. Bending stiffness is the product of actual segment moment of area, which takes into consideration the cross-section area and the distance from a neutral line or neutral plate, and the Young's modulus simplified. So we look here at the structural setup. So we calculate for each of the systems the actual segment moment of area, and then we ask if you would have a single stem with the same bending stiffness, how large must the stem be? And therefore we compared the area of these systems. So it's 4 times a single area here, 3 times, 2 times, and we compared it with a single stem with the same bending stiffness, which kind of area it must have. We take the area as a measure of the amount of mass to be invested, because they say it's a rod which doesn't taper, so the area gives us a representation of the mass which we have to invest, or of the energy which we have to invest. And then we say, okay, we make a ratio. Here we have the shoots, the intertwined shoots, which is the area of the intertwined shoots for a given actual segment moment area, and this is actually, this is a single stem which has the same actual segment moment area. How big must it be? And if this ratio is smaller than 1, then our system is much more efficient than the single stem. And you see, they are way below 1. Not surprisingly, as further they are away from a center of gravity, as better they are. So we have here 0.2, so they are 5 times more efficient than a single stem, 0.4, 2.5 times more efficient. This is what to expect. What's interesting is that with the number of stems, the effect decreases. The best effect we have is 2 stems, a slightly less effect is 3, and even less with 4 stems. Because with the number of stems, the effect decreases. And this might be a reason why you typically find braids in nature with 2 to 4 stems and rarely more than 6 stems, because then the game is lost. Okay, what did we do with that? We worked together with Ian Walker in the States, and he makes SMA elements, SMA robot searchers. These are shape memory alloys, and he had here 2 distinct of the shape alloy searchers, and he bends one, and this one can only reach the green cross. It can't have a higher curvature to fit to meet the red cross. If you braid them together here and make an antagonistic movement, this one makes this moves in this direction, that one moves in that direction, then you increase the curvature and you can even reach the red cross. So it's a very simplified thing just to show that braiding can really help to make kind of more of better soft robots. What we are doing at the moment, I can't show you pictures now because it's in the phase also of patenting together with the IIT in Pisa. They have developed a totally new robot arm made of polymer, which is based on this braided system because it has a discrete change. But this is really interesting. Plants normally have continuous changes in diameters, and probably because of growth process. But with braiding, you can have distinct regions. with a real stepwise increase or decrease. And this they really took over to this robot, and he can make movements which are you couldn't imagine them before. So this will come out hopefully end of this year. Now attachment. How do they attach? And there are methods to attach. You can have twiners, you can have tendril attachment with or without attachment pads, macro hooks, as here strychnos, micro hooks, branch anchor climbers, root hair climbers, or leading climbers. Resistant root hairs, tendrils, attachment pads, and twiners. I don't want to go into detail, it would be a lecture of its own. I just want to go to the twiners, because the twiners are inspiration for something else. But before I go to the twiners, I want to show you here again how twining works. They twine around the support, again stolen from David Attenborough, a time lapse, and you see high dynamics. Here is the old twiner, which is slipped down a bit, and here you see our role model, Dioscorea bulbifera, the air potato. It's the English name, I don't know, it's a French name, it's D. Anyways, and what does it do? And this is really nice. And this is work from Nick and my former PhD student, Sandrine Lisnard. She's now back in Montpellier. She was for quite a time in New Caledonia, and she worked at Missy Holbrook's lab on this twining, Dioscorea. And the twiner first makes this twisted stem around the support, but then it produces these stipules. And these stipules push away the twine stem from the support and dramatically increase the contact force, so that it can't slip down. You have to see you wind around something, a thread, but it's not fixed really. But if you put it under tension, this is stipules do, then it's fixed. And this we took as inspiration, made some additional tests, and then together with our colleagues from Stuttgart, from the Institute of Computational Design, we developed this kind of aesthetic device, which I will show you now. So the idea is force generation by twining stipules. Then we have to abstract it, the principle, to transfer it to computational design methods as a basis for 4D printed material systems. And then we make an implementation, we build the first prototype of this orthotic device. What is the background? Background is relatively simple. You want to develop a twining material. What did you do? You use a basic material, a kind of scaffolding material. We typically use ABS plastics, which is cheap and easy to handle. And then we have actuating materials. This is a copolymer, which consists out of a copolymer with cellulose fibers embedded. And the cellulose fibers shrink if they dry, and they expand if they are wet. And with the angle during printing, I'll show you later, with the angle of the printing of these kind of structures, you can nicely adjust the twining angle and all these things. And then we combine with this with so-called pocket mechanisms, which mimics the stipules, and they have to start later. First, you should have the twining around the arm, and later, when it's twined around, this pocket mechanism should come. And this is possible. I show you another example, because we have these layers which hinder water access, delayed, and so on. What did we do then? You see here, this is in a dry state, it's twined, and you see here nicely the twined fibers in the arrangement, and then it wraps up if it's coming into humidity. If you put it on your arm, I show you a video, it wraps around your arm. And then later, pocket mechanism starts and forms this pocket and presses against your arm. And as I said, the basic material is acrylonitrile, butadiene, styrene, ABS, and the actuating material is a copolyester embedded cellulose fibers. And what can it do? It can wrap around your arm just by the humidity of your skin, as we have shown here. It's not an arm, obviously it's a rod, but it's in a chamber where you have a humidity of about 70%, air humidity. Just wraps around and fixates itself. What's happening then? Here you have our prototype. We have now just a contact with a medical technical company who wants to build it. The idea is first, you have the helix mechanism. The helix mechanism, triggered by the humidity of the skin, wraps around your arm, your ankle of your finger. Then you have a wrist forearm splint. This is a primary structure providing a global support. Then the pocket mechanism starts with some delay and pressures and fixates it, as you see it here. So it will never slip. if you have ever an orthotic device, I had once problems with my knees when I was still volleyball playing. This thing never fixed. It was always gliding down. It was a nightmare. And here you can even equilibrate the pressure to the, let me say, feeling of the patient. Some accept higher pressure, others say, no, I don't want that. We can all fix it. And that's really great. And I hope really that we can come into production of this orthotic device. Before I go to my last moving example, I want to show you something which is really also inspired by Lianas. This is self-sealing. I told you that Liana stems, if they're old, they have to grow, and then they cause internal fissures. And this was the sealing of these internal fissures was our idea for self-sealing foam for pneumatic systems. There we were contacted by a company from Switzerland, and they built this nice so-called tenserity structures. They consist of a compression rod on top, tension cables, and they are put under tension by this rod, which is nothing else than a pneumatic cylinder with a slight overpressure only around 100 millibars. It works pretty nicely. You see, dismantled, it looks like that. A bridge which can carry 3.5 tons and span 8 meters, weighs around 150 kilograms, and can be set up in 1.5 to 2 hours. It's really a great thing. They already built structures architecturally. If you ever go to Montreux, it doesn't look that nice any longer because it's 10 or 15 years old and it's a bit dusty. But nevertheless, the roof of this parking lot in Montreux was built by these tenserity structures, and you can even light them by LEDs and make some kind of funny things in the evening from red over. It's like a disco a bit, but anyways. But a problem which is occurring with all pneumatic systems, you know it from your rubber mattresses, if a hole comes in, you lose. This is not a big problem here because of air pressure changes. You anyways have in the big buildings, you need compressors or stuff to keep to go on with the air pressure changes, because you look, the internal overpressure is 100 millibars. The changes in air pressure are easily 50, 70 millibars. You have compressors, but it's a real problem if you sell a bridge or a roof which is pneumatic, and you say, oh, there are holes in, doesn't matter, no problem, nobody will buy it. So you say, I came to us and said, do you have an idea for a self-sealing system for these pneumatic structures? And we had. And this is a Liana, stem cross-section of Aristolochia. When it's young, then it's this blue outer ring here. It's made out of sclerodermatous fibers. It's closed. And it stabilizes, makes them very stiff, the surgers. As soon as it attaches, a totally different type of wood is built inside. This is this wood, which has huge vessels, a lot of parenchymatic wood rays. It's very flexible. It only mainly serves water conduction, but it grows inside this ring, and therefore this ring is put under tangential strain, and finally it fissures here, 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 and here. And if these fissures would run through the outside, it would be perfect entry gate for bacteria or for fungi spores, and therefore there's a high selective pressure to seal them. And you see all of them are sealed. What does the plant do? It's very simple. The outer cortex here consists out of parenchyma cells. And you can imagine parenchyma cells like water-filled balloons, rubber balloons, under overpressure of about 1.5 to 2 bars. And as soon as the fissure occurs, they just swell into the fissure and seal it. So there's no biology involved, no growth. It's just physicochemistry. It's a disturbance in the stress-strain field, and they swell into the relaxin field. Later, if the fissure becomes larger because a plant grows further, then they start to divide and also can slightly liquefy. But we are interested in this very fast early process, which seals very effectively the fissure. What did we do? This is a functional model. Here is the membrane of the tenserity structure at the outside, and here we put closed cell foam on it. We cured it under slight overpressure, and we used for our testing polyurethane foam. And the idea is by curing under slight overpressure, the entire system is under slight pre-strain, and the cells themselves are also pre-strained with the overpressure during curing. And if a puncture hole comes in, the idea is air leaks out, but due to the pre-strain of the entire system and in the cells well and seal the fissure. And this works. Here you see this is a membrane, here you see our sealing foam, you see a nail was driven through here, you see the nail channel here, but here it's already sealed. And we can really, with this soft cell polyurethane foam coating, we can reduce the leakage in holes up to 5 mm diameter all times for 1,000-fold, slower, and in 99% we can entirely seal it. And this was really great. I'll show you a movie. This is a membrane with no self-sealing foam underneath. Here's with self-sealing foam. We blow liquid air over it to see how the air leaks out. First look at this one. I show it twice. It's punctured. Air leaks out. It comes back. Now look at that one with a self-sealing foam. You have to look carefully because it's very fast. It's punctured. Air leaks out. Now it's sealed. It's not nearly entirely or entirely sealed, it's also very quickly sealed, which is important, because if you're on a rubber boat, you don't want to hear the self-sealing process start in 2 days. It doesn't help really. And this is really great. And what we do, we calculated everything. I don't want to go into detail, physics. We defined a self-repairing efficiency, our flow, and our flow is calculated at 1 minus the airflow mass flow through a coated membrane, divided by the air mass flow to the reference membrane. If the coated membrane is entirely dense, no air leaks out, then it's 0 here, then our flow is 1. And if it's no difference, so we have no self-sealing effects, then it's 1, then our flow is 0. So our flow of 1 means entire sealing, our flow of 0 means no sealing. And if you look here, we have our flow values of 0.999, 0.998, so it's nearly entirely sealing. And this worked pretty nicely with a very small layer of this pressurized foam, and it's already on the market. Ramp-Kieshardt produces this Rakupur foam 33-1. I don't read it out. The problem is, why is it not really on a big market? It's relatively expensive, and for a rubber mattress, for example, a rubber mattress would cost, instead of, don't know what it costs now, 12 euros, 15 euros, it would cost 50 euros. And no one would invest 50 euros in rubber mattress. They would say, I buy another one with another color. And that's why it's at the moment mainly used in high-end rubber boats and special places. But it works perfectly and it's on the market. Now let's come to microscopic movements, the last 2 examples which I want to show you. And this is again a collaboration with Archimedes. And you see here, famous pine cone opening and closing. It's a B layer. It's said, but it's much more complicated. I don't want to go into details, but it's really interesting. And what we did, we analyzed how nature was 4D printing. We did microcity analysis, where we looked at the different structures, at the different tissues, how they deform with a microcity, high resolution microcity. Then we did measurements with Aramis, where we can exactly measure the displacement and also the strain on the upper side of the lower side of the scale. And what's more, the question is why are engineers so impressed by microscopic structures? The reason is manifold. They are entirely passive, no energy consumption. They are a sensor, actuator, and reactive modal element and support structure and material system, which have a high level of functional integration and display an extraordinary high functional resilience. And the test is time. And this is perhaps especially interesting for the paleontologists here. We looked at fossil cones. This is Catillaria from the Miocene, between 11 and 16 million years old, and this is a fossil pine cone from the Emil interglacial about 120,000 years old. And here you see the changes in movement from dry to wet. This is a recent and extant Pinus silvestris, and you see as well Catillaria here in red, as the fossil pine cone, have exactly the same movement pattern. They are slightly less in the angular change, but they have, after 50 million years, they do exactly the same, the charcoalified cones. Why do we have this distance? It's probably due to the fossilization process that you have tiny minerals embedded which hinder a bit the movement, but in principle it works even after 50 million years. We do then, and here you see it nice, we printed it again, body printed. We used again, this is a white stuff, ABS is basic material, and this copolymer here is cellulose in, we printed, and what can we do? Here you see a real pine cone scale of Pinus wallackiana, and it's not only bending down, if it's closed at the cone, it's also folding and stabilizing V-shaped, and then it flattens and goes down. We can exactly print the same motion pattern here with our artificial pine cone thing. Our wish, we want to change this is a state-of-the-art convertible roof system, Wembley Stadium, which I like very much, but frankly spoken, it's technically totally overcharged. has a high energy consumption, has high cost for construction maintenance, and often blocks. But we want to make a smart building skin. First, nastic movements, that the scales open and close if it's wet or dry. This is what a pinecone does. But we also want to integrate Hobistic movements so that they bend with the sunlight, so that they shade. And this is what we're at the moment doing and trying to do. And this can be also used for soft machines. You can be heavy. I'm coming to an end. This is my last example. And this is the silver thistle. Silver thistle shows a wonderful uniaxial three-phase motion of the involucral bracts. This is not a flower, it's a flower head. You have here the many flowers inside. This is an asteraceae, and these are the bracts. And the bracts, if they are dry, they fold out so that pollinators can come. If it's wet, they close. And here you see the movement. And you have two movement phases. First, in 2 minutes, it's bending that way. Then in 10 minutes, it's stretching. Then in about 15 minutes, it's bending inwards. And that we try to understand it. And here you see what's happening. We put rain on a flower, artificial rain. And the first thing is the relative angle. Yes. It's a gardener's rain. And the thing is, which is very helpful for us, the relative angle goes more or less linearly with the relative humidity. So it's directly related to humidity. The next thing is, and this is also helpful, that it starts only if the drying out has lost about 38%. So the first drying out phase, the reddest mass, nothing happens. It's drying, and only if 38% is dried out, then it starts, which is very helpful. It's not an immediate change. You can play around with it when you have a new start. And here's very quickly again how it looks like. Very simple, the bract in cross section. You have here the parenchymal cells, which are dead. It's only, again, like the pinecone, it's a totally dead system. It's only because you have cellulose microfibers in the cell walls which extend and contract for the humidity. Then you have here a kind of cuticle which blocks water access, and you have down here a system which slows down water access. And what did we do? We tested it. Here is an untreated one, and here we block the axial side, which is already blocked in the nature. So nothing changes. And here we block the abaxial side and both sides. And you see nothing happened, but now I have to go to 50 times. With a much time delay, if you block the lower side where normal water has access, it even starts. So it's not totally blocked, it's delayed. And this is interesting, and this we use here against the curves. Unblocked, blocked top side, exactly the same. And here, lower side blocked, much time delay, but at the end, it comes to the same angle. And if you block both sides, nothing happens. And this was the inspiration. How can we play around in a 4D printed system? We can change the thickness of the active layers. We can change the porosity of the mesostructure of the active layer. Higher porosity allows higher bending. We can block the surface areas access to water by absorption and desorption, and we can delay it. And this is exactly what our colleagues did from Stuttgart again. This is Jasmin Harmoni, it's a PhD work, or part of a PhD work. Here you have 4 actuating layers, which bend, shrink, or expand. Then you have a restrictive layer, which doesn't let water slowly in, and here you have a blocking layer, which blocks water totally out. And what did we do? For example, here you have a system without sequential opening, and it can interfere, you see, it can block. And here you have one with sequential opening. The outer two are opening faster than the inner two, just by the inner two are more delayed in water access. It's exactly in the same humidity range. You can just by clever material design change the actuation of different parts, which are printed exactly the same. And this is really, it's not a material any longer, it's a machine. It's a soft machine which you can build, and we build an even better soft. Just tell me. No. And you can even build better soft machines, and this we did. It's a rolling locking mechanism. You have to imagine, this is the same material, just with different arrangements of blocking, delaying layers, and actuating layers. And the idea is, if you put it into humidity, and then first this thing rolls up, closes. With the slit here, it goes over these two strips, and then with the delays, the strips fold outward and lock it. And it works. And now it's locked.
That's great.
It's really delayed. You can really build tiny machines in a range of centimeters, millimeters. You can print them, and they do exactly what you want to do. And with this, I'm at the end. Thank you for your attention. It might be slightly overtime. Sorry for that.
No, we're starting late.
This is my group. This is the funding we get. And if you are interested, you'll find a lot of additional material in these internet pages, and I will hand over to Annabelle the PDF, so you can look also in the PDF again. And if you are interested, here is a very nice digital tour, with a virtual tour through an exhibition we had 3 years ago now at Stuttgart, and it's really nice. It's all inspired architecture, plant-inspired architecture, and that's it. And thank you very much. And if you have questions, please ask. You can't believe it. It's enjoyable. Hearing applause and then only sees his hand. Thank you very much for that.
Thank you, Thomas, so much. That was fascinating.
Thank you.
I thought we could take questions from the room first of all, and then I'll have a look to see if there are any questions from people joining virtually. So if you could repeat the question when you receive it from the colleagues, because then everyone can hear.
Okay.
I have a question. Yeah. So there's a lot of motion in your plants.
Yeah.
You're exploiting. So why do you think you're very successful at using plant motion in doing Bioinspire design, and you're very poor? We talked about this.
Yeah.
You're very poor at using animal motion. Yeah. Mm. So why are we so bad? Is it just because you guys are so smart?
Yes.
Could you repeat the
Yes.
question?
No, I repeat the question. Anthony is asking, why are plants so wonderful role models for motion in architecture and other smart materials, and animals, which are normal mobile organisms, have, I wouldn't say much less, but a little bit less success. The reason is funny. If you go back to the 60s and 70s, everything was inspired by animals. Flight, walking robots, 6-leg, 8-leg robots. But I have to say, there is, in my opinion, is a mistaken thinking. One mistaken thinking is that if you look at a 6-leg robot built in the late 70s, early 80s, the new ones look not very much different. Even the fantastic ones of Boston Dynamics, the structure looks the same. What they did, they implanted much more calculation power. And this is tempting for biologists who work with animals, because animals have a central brain. Plants don't have it. Plants do everything delocalized in smart, energy-consuming materials. So embedded energy, embedded intelligence in materials. It's much more obvious in plants than in animals, because in animals, oh yes, I'm married. But if you look in detail, animals have the same embedded intelligence and energy in their systems, but nobody looked at it. And I totally agree with you. It's a pity that at the moment the animal side, in my opinion, has a bit lost pace compared to plants. One other reason is, and we discussed it in the afternoon a bit, that a lot of fantastic robot work is not feeling itself in biomimetics. They are roboticists, they are not biomimetics. The same is in neural networks. They are artificial intelligence people. They are, in my opinion, perfect biomimetic examples. But if you say you are a biomimeticist, no, I'm an artificial intelligence person. This is the other thing. And for architecture, I have to say their plants have a big advantage. If a storm comes, hail goes down, each animal hides itself, goes in a burrow, goes away. A tree has to withstand it, exactly like a building. Therefore, plants for architecture are the prime models, in my opinion. This is part of the reason, but the other reason really is this. It sounds funny, it's that one of the best things which happened over the last 20 years, the increase in computational power decreased the success in animal bioinspiration. Yeah, change it. It's easy to change it because I spoke with colleagues who work with spiders. There is so much embedded intelligence in the spider lectin because not everything was a spider leg is controlled by the ganglia. Spider is also ganglia, I don't know. It's a lot is automatized, but nobody uses it. So, yeah.
And maybe also due to the structure made by fibers, different network fibers, so with some different glue versus the different environmental factors, humidity, wind.
Now this is here asked because of the fibrous materials which plants react easily to humidity. That's again, it's more or less on the same thing. Plants are vegetables.
Yeah.
They react and they can't be. It's not true. Carnivorous plants decide a lot. I think the Venus flytrap and the water trap are the most complex structures on an organismic level without a centralized brain. They decide, they have a mechanical memory and all and so on. But at the end, plants are much more reactive to the environment as animals. Animals have I don't want to call it a will, but animals have a behavior, which is in plants much less visible. And the other thing is, and you are right, all structural materials in plants and animals, or most structural materials in plants and animals, are composites with fibers in it. Cutin, cuticles in insects, plants stay in bone, but these are inside, typically inside of the body in vertebrates, or they are covered in insects. And an insect leg, maybe I'm wrong, but an insect leg doesn't move with humidity. It's more or less stiff. And this is a basic difference. Animals have joints, either joints as vertebrate or joints as insect, and therefore they have muscles. And this is a totally different system we use, and I think this jointless elastic motion has a big advantage because you do not need maintenance, because nothing happens. Yeah. Look at your door. What makes problems? The hinges. But stuff like that. If you don't have a hinge, you have no problem. And this is a big advantage in these elastic structures, global. They are mostly delocalized. There are some localized structures, but at the end they're also delocalized. We worked a lot on the lever arms in sage, in salvia, and they have bands, ribbons, small ribbons. And these ribbons is really funny. They can really change the force you need to trigger them by changing the turgor, the cells in the ribbon. And this was an idea we never went much on for medical microsurgery instruments, because my daughter, she's a medical doctor, and she says each surgeon wants to have a different kind of how fast you have to press it, and then you could adjust it just by changing these things. And this I think is at the moment a problem, but I think animals come back, definitely. If you look perhaps in a more broad way on their materials and their structures, and not only on the kind of brain-guided motion.
Any question? I had a question about the lianas and whether there's any chemical effects or communication. We're hearing more and more about sort of chemicals between plants and communication. Is there any aspect? I mean, you said it happens in a dark room anyway, but do you think there's any kind of attraction or between two lianas themselves?
There is a lot of chemical warfare and chemical communication in plants. If you mow your lawn, the grass sends off chemical structures which calling the other grass leaf, good God, I'm killed. So it's really, you can measure it. It's really like if you chop off an arm of somebody, but you don't see it. This is one thing. In a canopy, you know there is a canopy shyness. So you have always a tree canopy in a tropical rainforest, and the other trees don't grow into this region. And for a long time, it was thought it's purely mechanical. So but it's chemical. One tree says, I'm here, never go in. There is a lot done. With lianas, we know relatively little. We know that some of the reactions of the tendrils, the twisting is chemically, it's internally chemical cascade, as known. But this is what we do with colleagues from Israel. We have found that lianas, if they make circumnutations, and this is a support, and this is a liana. They touch the support and never they fix at the first touch. They go away, and they fix at the second or third touch. And in my opinion, they screen the surface. I have no idea how, but they screen the surface. If the surface of the support is good enough, And some, for example, they never grow an aluminium. We never managed to let them grow in aluminium. So they seem to have a chemical signal, aluminium is no good. Because it's poisonous or something like that. So I'm convinced, to your questions, that there's a lot of chemical interaction between Liana and support. At the moment, we just don't know it.
Maybe it's a kind of signal to stimulate into some liquids, make adhesions.
This is one aspect. You are true that for the first one, there is support, and then you have some time to start. But as they say don't attach to some supports, there seem to be also kind of communication of the support type. Perhaps they also sense if the support is stable enough or it's very fragile. So there's a mixture. This is typical for Liana, the mixture of chemical information and mechanical information, and we try to understand more, but we are just at the fringe of understanding these things.
It's fascinating. There aren't any questions in the chat, so if there aren't any other questions from the participants in the room, we can maybe wrap up. It's all just coming. Thank you.
Come over, yes.
So thank you so much, Thomas. It was a fascinating talk.
Thank you very much for the invitation.
Having you here. So we'll be putting your presentation, the recording online. And as you said, you've got some PDF versions that we
just
can share.
sticks, then you can also share a PDF version.
Excellent.
Everything. A lot of citations are in. You find nearly all papers on Google Scholar.
Great.
If you don't have access, just write me an email and I send it or go via how it's called ResearchGate or something like that. Absolutely easy.
Excellent. Thank you very much.
Thank you.
Now I found a new system for much better. It's 360 degree. Yeah,